What's up, everybody? Welcome back. We're going to be starting on a new problem today for fluid mechanics. This is 4 part B. The main goal of our problem today that we're going to be working on is to find a set of dimensionless groups from the change in pressure, density, viscosity, length, diameter, and volume to describe the flow in a horizontal pipe. So we're going to do a few steps to get there, obviously, but we'll find these dimensionless groups, and then we'll use these to derive the Reynolds number as well as a Bernoulli's equation for a horizontal smooth cylindrical pipe at the end. We'll be jumping back and forth today between the whiteboard and the computer just to make sure that we cover all of our bases, and it's going to make our problem a lot easier to solve. So let's find a set of dimensionless groups. What is a dimensionless group? Well, a dimensionless group is a set of variables in some relationship to each other without dimension. Now, in these 6 variables we have here, we have 3 main dimensions or units that we're going to try and cancel out of each other. We have units for mass, like our kilograms. We have units for length, like meters or kilometers or something like that. And then we have units of time, so seconds. And all of these variables we'll see in just a minute come from those 3 units, or a combination of them. And I guess we can get started. To find these dimensionless groups, we're going to use something called the Buckingham pi theorem, which has us start by writing a matrix of all these units out. So let's go through each of these units, pressure, and so forth. And we'll write down what we know the units are, and then we'll make that dimensionless matrix. Or we'll make that matrix, and then we'll find the dimensionless groups. Okay? So pressure, first of all, pressure has units we know of, well, it's a force over an area, so like a Newton per meter squared, right? So a Newton per meter squared. And remember, we're trying to get all of these into units of like kilograms, meters, and seconds. So I guess we got our meters there, but what's a Newton? Well, a Newton accelerates 1 kilogram, 1 meter per second, right? So a Newton is equal to a kilogram meter per second squared over meters squared. We get kilogram meters cubed over second squared. Did I do that right? Let's see. We get Newton. Newton's force equals mass times acceleration, kilogram meters per second squared. Divided by, oh, that's wrong. Okay. There we go. Glad I checked it. At least something didn't look right there. Okay, so we have kilograms over meters, seconds squared. Okay, so that's pressure. Let's do density next. So density, we know is equal to mass over a volume. So that would be something like a kilogram per meter cubed. We're good there. Good there. We have mu. Mu is viscosity, which is in units of Pascal seconds. Okay. So what is a Pascal? We have Pascal's a unit of pressure. So kilogram meter second squared times seconds just equals kilogram over meters second. Okay, we have units of length. That's just like centimeters, right? Diameter. Diameter is also just in units of length, meters, right? How did I say diameter before? If I didn't say diameter before, D is diameter in this problem. Diameter of a pipe, right? And then we have V. I think I said volume before. V is not volume. V is velocity. So meters per second. I need to be careful with my V because that looks like an uppercase V to me. I need a lowercase v for velocity or else I'll forget it. Okay, so we have velocity in meters per second. Diameter in meters, length in meters, viscosity, kilogram per meter second, density, kilogram per meter cubed, and pressure, kilogram over meters times second squared. Okay, so let's create our dimensionless matrix, I keep saying that, let's create our matrix now for all these units. So we have kilograms, meters, and seconds. Okay, and then we have the following variables. We have pressure, density, mu, L, D, and velocity. Okay, so now what we're going to do is we're going to write numbers in each of these cells that correspond to the power to which the unit is raised to in the dimension for that variable. Okay, so for example, let's do an easy one first. Length. Length is in meters. So meters has a power of 1 in length and no mass and no time. The same would be for diameter. Okay. Meters per second, however, has meters raised to the first power and seconds raised to the -1 power, and nothing for kilograms. Okay, and then we have viscosity, so kilograms over meters seconds. So kilograms over meters over seconds. Then we have density, which is kilograms over meters cubed, no seconds. And then we have pressure, which is going to be kilograms over meters over seconds squared. Okay, and that's going to be our matrix that we're going to use to apply the Buckingham pi theorem. Now, what the Buckingham pi theorem is going to do is have us set up a linear system of matrices. If you're familiar with your linear algebra expressions, we're going to solve the matrix equation AX equals B, but we're going to do that on the computer. So I'll just say let's pause here, and I'll join you on the computer here in just a second. Okay, so welcome back. We're here in front of the computer. We're going to solve that matrix that we just came up with, and again, the reason we're doing that is, remember, we're trying to find the dimensionless groups from those 6 variables. Well, it turns out, there's some number of dimensionless groups that we can come up with from those variables, but we don't know how many. Well, the Buckingham pi theorem tells us that the number of dimensionless groups that we can come up with from those variables is the rank of the matrix we just wrote down. Okay, and the matrix we just wrote down, remember, is it's the matrix of the powers of the units that go into the variables we're interested in. So let's very quickly get that matrix back into the code here, and then we will use some functions of numerical Python to solve for the rank of that matrix. And we'll go from there, okay? I will try to put a picture of the matrix that we just solved for on the video screen somewhere in editing. So I think it'll be like right here. I'm not sure if that worked at all, but with that, let's get started. I'm looking at it still in front on the whiteboard, the matrix that we just solved for, so I'm just going to copy that down in here. We need to import numerical Python for all these arrays. So okay. And then let's go ahead and I'm going to write all these things we just came up with down. So for pressure, we said we had units for kilograms. We had power 1, meters -1, and seconds -2. Okay. For density, we'll call that rho. We used the Greek letter rho there. We had kilograms, which is, we got 1. We had meters cubed, so -3 per meter cubed, kilogram per meter cubed. Seconds, 0. Okay. Oh. For, we'll call this mu. For viscosity, we have kilograms per meter, per meter per second. For length is the next one we had. We have, that's an easy one. No kilograms, just expressed in meters, and no seconds. And it's going to be the same thing for diameter. Okay. And lastly, velocity, we'll call that little v. We have no kilograms, but we do have meters per second. Okay. And that's good there. Let's go ahead and put this, I'm going to stack these into the matrix form so that we can see it how we saw it on the whiteboard. So let's go ahead and do that. Let's call this our dimensional matrix. Okay, and this is going to equal, we're going to column stack these. E rho mu L D and V. Okay. Store those as float variables. Okay. So let's see what that, let's make sure we got that right. Okay, so there you can see the array that we just came up with on the board. I think it looks identical. I'm just gonna check that. Yeah, same one we just came up with on the board, okay? And okay, so these are our columns here. We need to find our dimensional groups somewhere in here. So the rank of this matrix is going to tell us how many dimensionless groups that we can get. And then from that rank, we can pick our core variables and our non-core variables to kind of cover that spread. So let's go ahead and find the rank of this matrix. We'll call it rank. Actually, we don't even need to define it as a variable. Let's just solve for it. We're going to use np.linear algebra dot, what is this called? Is it called a rank? Oh, matrix rank. There we go. And we just need to find the rank of our dimensional matrix. And we get 3. Okay, so that means that we can come up with 3 dimensionless groups from those 6 variables, knowing that the variables are expressed by these powers of our kilograms, like our mass units, our length units, and our time units. Okay, so 3 dimensionless groups. What are they? Let's see, how do I want to do this? So let's pick core variables first. So our core variables are going to be 3 of these variables, any 3 of these variables that cover basically all of the units that we have. So we have units of mass, units of length, and units of time. Our 3 core variables need to at least have one of each of those in it. So we couldn't choose, for example, L and D because they're both the same. They're not linearly independent from each other. We are going to choose, I believe there was a recommendation in here to choose a certain variable. I think, okay, we're going to choose L, rho, and V is the ones that we're supposed to choose, I guess, for this problem. So rho, L, and V. So I'm just going to call that our core variables are rho, L, and V. Consequently, our non-core variables are, looks like we have mu, P, and D left over. Okay. I'm just going to put that as a note in there. So what we have to do now is set up this matrix equation to solve. Basically, our non-core variables can be expressed in terms of linear combinations of our core variables. So because the number of independent combinations that we can come up with out of these variables is only 3. So the other 3 have to be combinations of the original 3, basically. So let me think. I'm gonna make a matrix of our core variables. This will be like our A matrix in the matrix expression AX equals B. So I'll just say core equals, or I'll call it like core variables. And this is gonna be I'm gonna stack the variables again, just like we just did. So it'd be like MP dot C, and then we set our core variables. What were they? Rho, L, and V. Okay. And then you'll be able to see here, if I just write like a core, see what that looks like. Yeah, so there's our matrix there, and you can see like we have rho 1, -3, 0. That's the same as our row up here, 1, -3, 0, 0, 1, 0. That's our length, and then velocity 0, 1, -1. Okay. Now, I think the best way to do this would be to open up like a drawing tool really quick just to explain this. Let's see if I can snip this. Hopefully you can still see this. So, okay. Okay, so I think you can still see this here. I'm gonna make this bigger. So this is our array, and we're solving the matrix equation effectively like AX equals B. Now, in a dimensionless group, the sum of all of the exponents equals 0, right? And that's effectively what we're doing here. And what I mean by that, so like sum of all the exponents. So we had mass, length, and time. If I have like meters over meters, that's a dimensionless group, right? Because we have meters to the first power and meters to the -1 power. 1 plus -1 equals 0. And if you can do that for each of our types of variables, we'll be able to solve this equation. So what we have here is AX equals 0. Okay, but we have more variables than we need. So what this really means is we have like, this is our A matrix right here. This is A. So our A matrix times some combination of mass, length, and time okay, plus a non-core variable will equal 0. We can rearrange this linear or algebraically. and we get this. It's equal to the negative of a non-core variable. Okay, and this makes sense. Some linear combination of our core variables equals our non-core variable. Okay, and this is how it looks in the matrix equation. So this is what we're going to try and code for, and we're solving for this right here. We want to know what that combination is. Okay, so let's go ahead and do that now. So to do this, we're going to be using np dot, what is this called? Linear algebra dot solve. All right. And when we do this, we need to, let's see what we need to put in. We need to put in our matrix equation, and then we need to put in b, because we're going to try and solve for x. We need a and then b. So remember, our a matrix is just this core variable matrix. And then b is what we're trying to solve for. So it's the, and remember we moved it over to the other side, so it's like negative, and it's this array, which is our first non-core variable. Let's do mu first. Mu is 1, -1, -1. We can just put mu there. Okay. Actually, I'm gonna do an easier one first. Let's do d. Okay. And then let's see if this works. Okay, great. So we get this is the solution. 0, -1, 0 is the x vector solution to that linear, or to that matrix equation. So so basically the interpretation of this is, it's saying, go back to my, I closed my snipping tool. I'll explain the applications of this once we solve for all of them, and we're going to hop back over to the whiteboard. I think that'll be easier. So let's go ahead and do the rest of these, but that is the solution for the first non-core variable. It's that linear combination. I'm gonna be lazy and copy this. Let's do mu next. Okay, and lastly, oh, pressure. It's the last one. Okay, that doesn't look quite right. Okay, I don't know why these are showing up like this, but you can see we get -1, 0, and -2 effectively. Okay. Okay, so I will I'm going to take these solutions, transfer them up to the whiteboard, and then we're going to apply these to our problem and get our dimensionless units from it. Okay, so we'll see you in just a minute. Okay, so thanks for sticking with me. Let's go ahead and interpret our results from finding the solutions to those matrix equations. We're going to finally find our dimensionless groups here. So I've written down the solutions that we came up with just on the computer. Remember, our core variable, or our A matrix here, was made up of the core variables, rho, or density, length, and velocity, and then we used our non-core variables here, diameter, mu, and pressure. And then we solved these equations, and we got the following results. So when we solved for the diameter one, we got the solution as 0, -1, 0, mu, -1, -1, -1, and then p was -1, 0, and -2. What does this actually mean? It means that for this set of variables, these are the powers to which we can apply to these variables and then multiply by this variable to get a dimensionless group. For example, diameter. we have diameter times density raised to the 0 power, okay, so that doesn't matter, length raised to the -1 power, and velocity raised to the 0 power. It also doesn't matter. And that's saying that that is a dimensionless group because the powers of the mass, length, and time of that final unit will add up to 0. Let's see what it works out to. So this is d over L, right? And we know that diameter is in meters and length is in meters. And look at that, our units will cancel out. Now that's a simple one, obviously. That's our first dimensionless group, though, that we can come up with, d over L. So this is number 1. Number 2, for our mu. So we have mu times rho raised to the -1 power, L raised to the -1 power, and velocity raised to the -1 power. Okay, this equals mu over rho L V. Okay. Now we're going to work with that one in just a second. So I'm going to leave that there. But our third one here is for pressure. We have pressure times rho to the -1 power, L to the 0 power, and then velocity to the -2 power. Okay, and this is equal to pressure over rho V squared. Okay, and that's our third dimensionless group. Okay, so let's jump back to that second one. Now, you'll notice that this one is eerily close to what we call the Reynolds number. And the Reynolds number is also a dimensionless group. So if I said we can only have 3 unique dimensionless groups out of this, how can there be another one? Well, the Reynolds number isn't actually unique from these 3. These 3 are unique to each other, but there's other dimensionless groups that we can make. There's a lot of them, in fact. But they're all just combinations of these 3, and the Reynolds number happens to be one of them with this set of core variables. If you switch your set of core variables and your non-core variables, you will get different dimensionless groups, but they will all be multiples of the 3 that you come up with, okay? Every existing one. So the Reynolds number is rho VD over mu. So how do we come up with this? This is also a dimensionless group. How do we come up with this as a combination or a linear combination of these dimensionless groups? Well, you'll notice it's really close to this one. Mu, rho, L, and V. And then if we take, let's see how we can do this here. The only thing that's different is the D and the L. It should make sense if you think about it for a second. What we can do then is we can take that second one we have, which is mu over rho L and V multiplied by D over L. Oh, excuse me. Let's do that. Multiplied by D over L to the -1 power. So really we're dividing by D over L. And then we can raise this to the -1 power. The reason we can raise these auto powers is because they're dimensionless. If you raise a dimensionless unit to a power, it's still dimensionless. If it had dimensions like meters or something like that, and you raise it to a power, that wouldn't work. You'd get meters to like meter squared, meter cubed. That's a different dimension. However, these are dimensionless, so we can rearrange them, put exponents on them however we want, and they'll still be dimensionless. So we perform this operation. This is just a linear, or that's not linear, but it's a, oh yeah, it is linear. It's a combination of our second dimensionless group and our first dimensionless group. So if we take this one, the second one, and we divide it by the first one, we get mu over rho v d, and then we put it to the -1 power, so we just flip it, right? And that just equals rho v d over mu, and that's the Reynolds number. And so we get another dimensionless group as a linear combination of our first dimensionless groups that we came up with, the core variables we found. So you can do this as many times as you want in any combination you want, and you'll always get a dimensionless group. So these are our 3 dimensionless groups. Okay, the last thing we have to do now is we're going to plug this all into the Bernoulli's equation and see how this all works out there. So I'm going to give us some more space here on the board. I'll leave our dimensionless groups up here for reference. Oh, I erased one. So our first one was, I think it was, what, D over L? Okay. So the last thing we want to do now is we're going to approach the Bernoulli's equation for a horizontal cylindrical pipe. And we're going to kind of see how these dimensionless units play into that equation. Okay, so bear with me here. We're going to write the Bernoulli's equation out for this horizontal pipe. Recall that Bernoulli's equation is like this. We have delta P over rho plus, we would have a component here for the change in potential energy, the change in height, and then also the change in kinetic energy due to a narrowing or widening of the pipe. But for this problem, we're going to assume a horizontal cylindrical pipe, constant diameter, so those terms really will equal 0. Okay, so they're 0 there. Okay, we don't have to worry about it, but they would be there normally. And remember this equal, we derived this in our last video. This is equal to a whole bunch of stuff on the other side that we call the negative, this is the frictional heating, right? And we kind of do this fancy F. Okay, and we kind of derived where that came from in our last video. Now, F is equal to 4 times the friction factor. This is the fanning friction factor. I'll go over that in just a second. Fanning friction factor times L over D times V squared over 2. Okay? And I'm going to show you now with the dimensionless groups we just found as a relationship of those 6 variables that this Bernoulli's equation is literally just a bunch of these dimensionless groups thrown at each other. And that's why this equation works, okay? Hey everybody, I apologize for the cut in the video really quick. I realized when I first filmed this, I actually gave the wrong expression for the friction factor here. So that's why the jump cut exists. So just bear with me as we continue this problem. So I've rewritten down our Bernoulli's equation here, and then our 3 dimensionless groups that we've just come up with. And remember, we're trying to show that this equation is just a combination of these dimensionless groups that I've worked out, right? Okay, so let's talk about this friction factor. So the friction factor is equal to 16 over the Reynolds number, and this is the fanning friction factor. So there's the fanning friction factor and the Darcy friction factor. In this scenario, we're using the fanning friction factor, which is 16 over the Reynolds number. Okay. Now, how is this expression just a combination of our dimensionless groups that we found out? Well, let's do some algebraic manipulations and we'll show just that. So, we can rewrite this. We have delta P over rho equals, we have 4 times 16 over the Reynolds number divided by 2. So, we take all those into account, we get 4 over 2 is 2 times 16 is 32 divided by the Reynolds number. Okay, so we get 32 divided by the Reynolds number gives us mu over rho VD, okay, times V squared, right? Okay, oh, and of course we can't forget L over D. Okay, and so you can start to see these dimensionless groups come together here. So we have D over L looks awfully familiar to L over D. One's just the reciprocal of the other. If we rearrange some of our terms here, we can divide both sides by velocity squared, and we get delta P equals rho V squared. Delta P over rho V squared equals 32 times the inverse of the Reynolds number, which is mu rho VD, and then times L over D. And so you can see now that with a constant out in front, we now have our three-dimensionless groups here, as we found them here, and they're just a combination of each other. So I think we've effectively solved the problem now. We've shown that our Bernoulli's equation with the frictional heating is really just a combination of our dimensionless groups. And that's all for today's video. So thanks for joining me, and we'll see you next time for the next part of our homework. Thanks.